So we got involved with the satellite business about 11 years ago, sort of accidentally, but it's worked out to be pretty exciting. And we have a current satellite that's in orbit. It will be 2 years in about 2 weeks that it has been in orbit. It's been operating successfully. It's part of NASA's Alana program, the educational launch of nanosatellites, where you submit a proposal, and if they like what you're doing, you get a free ride into space, and on various types of launch vehicles. We were launched on an Air Force rocket, Minotaur 1. I'll show you more about that near the end of the talk. And so they started this in 2010. We were in the first group that was selected. We have a single unit CubeSat. The CubeSat is a standard for the external dimensions and mass of a small satellite, so they could all fit in the same kind of launch box. The single unit CubeSat is approximately a 10 centimeter cube, 1 1/3 kilogram maximum mass. And we have a single unit CubeSat, what's called a 1U CubeSat, for our first satellite project. And we're testing components that we had hoped to build a satellite going to the moon. It was probably a pretty far-fetched hope, but in fact we are now working on a satellite that's going to the moon, which I will describe a little later. In this launch that we were involved with, the Atlanta 4 launch, there were 12 university CubeSats, 2 NASA CubeSats, and 14 Air Force CubeSats. The Air Force ones were mostly classified, so we don't know too much about them. I have a little bit of data on them in a next slide. 4 of the university CubeSats had some manner of operation. 8 of them were never heard from at all. Except for ours, I think they were all programmed in C. It says something about the language they were using. One of them certainly fried their batteries the first day due to a software error, actually a couple of software errors. The other ones didn't work, we really don't know why. A second one had some partial contact from during the first week only, and then the third one operated for about 4 months successfully from Morehead State University and then died. And we've been operating for almost 2 years. We are now working with Morehead State University on the next satellite, which we're doing the flight software for. As I said, ours, it says here, ours, as many Vermonters do, took a 2.5-month winter vacation. Turns out there was a hardware issue with a power board that was being supplied where a pull-up resistor on the data line that was there that shouldn't have been there, and it made the data line sort of marginal. Fortunately, it worked when we deployed our antenna, and we then noticed we weren't getting from the power supply telemetry data that we should have had, so we figured out there was a problem with it. And then a couple of my students, without talking to me, decided to reset, and the software had a little design issue in that it looked for some data coming from this antenna board to complete the boot up process, and didn't have any alternative path, so it never actually timed out and just went on. It just stayed there in loop, and this was not getting any data for a while. So during the winter, from December and January, after the launch, it sat there in loop, not doing much else, and then finally some data got through and it came back to life and has been running ever since. There were reliability issues, design reviews. We had too small a team to do design reviews, even though we know we should have been able to, we should have done them, but we didn't have the ability to do that. At most we had 5 people working on the satellite. Most of the time, less than that. The last 3 months before launch, 2 people, myself and 1 student who was writing the software. He wrote about 80% of the 10,000 lines of code. Our language selection, I think, was really a primary reason that we were successful and others weren't. We used Spark Ada. We were using Spark 2005, which was what available at the time, and Ada 2012. We now have redone that software in Spark 2014 and are now redesigning it and expanding it, as I'll describe in a little bit. We used a repository called Assembla. Other teams didn't do that. The team that fried their batteries, in fact, had a little issue with a repository, and instead of loading their flight software on the CubeSat, they loaded their test software on their CubeSat and delivered it for launch. And they also had problems with the way they designed the software that was loaded, whether it was the flight or not, and they had problems with their testing. They tested to see that the batteries didn't overcharge in their laboratory, you know, where you might have about 1 watt per square meter coming on the photovoltaic cells, and in space it's about 1,400 watts. I tested ours with 2 halogen bulbs right down on the photovoltaic cells, certainly getting up in the 1,400 watt range. The other thing is we had an antenna by ISIS, a company in Holland, not Syria. They had an electrical model of their antenna, which was $2,700. It's a lot of money. The antenna, which is deployable antenna, was about $7,000. And I spent the money so that we could fully test a software that would deploy the antenna without having to actually deploy it. Some people did that, and after reading the instructions for repacking the antenna, I decided it was worth $2,700 not to have to do that. And so we got this, and so instead of deploying antenna, it would light up LEDs and showing that your software was communicating with this antenna board, which had 2 CPUs, redundant system, and we did do that to make sure that our deployment was reliable. If you don't deploy your antennas, you've got a dead satellite. Again, most of them use C, and Ada alone will cut the error rate by a factor of 10, and with Spark by a factor of about 100. And students who had not programmed in Spark Ada became proficient enough to be useful in about 2 weeks. So I've talked to people at various conferences say, well, we're using C because we can't hire Ada programmers out of college. And my argument is you don't need to. You can just hire people who understand software engineering and you can have them using Spark in a couple of weeks. And some of the things that Spark Ada is used in, I went to the Ada Europe conference on an Airbus this summer, and knowing it was nice that the engines were being controlled in Spark. Various other systems are shown here, the Eurofighter, the Harrier, Lockheed Martin C-130J, the UK Air Traffic Control System. They're doing some interesting things. They have about 250,000 lines of code, and they're doing incremental testing with Spark, so they don't have to run all of the software through. As they make changes each day, they can run Spark on the changes they made, and it takes about 10 minutes, a coffee break worth of time, and they're back in operation again, rather than having to run through the entire 250,000 lines, which takes a number of hours, I think. I don't know the exact time. So this describes the software in our current satellite. So almost 6,000 lines of code, 4,000 lines of comments, 2,843 are Spark annotations. So those are really part of a program. They're telling the Spark tools what we intend our software to do, and the Spark tools go through and they generated 4,542 verification conditions that needed to be proved to show that our software was doing what we had intended. All but 102 were approved automatically by the prover. That was available in Spark 2005. Other provers are now available, and the UK system are getting 100% automatic proving for their verification conditions. So we hope to be doing that on our new project. So we suppressed all the checks because we proved using Spark that we couldn't have any runtime errors in our software. We had some C. Part of it was a C library to access our SD card that we purchased along with some of the hardware. And so we don't know I don't have the data on how much of that was actual C code, but that included the blank lines, the 2,200 lines. So as I mentioned, we would be able to do 100% proving in the future. Our new satellite, we're calling the software Cubed OS. We're trying to develop a general purpose satellite software package that has a whole bunch of the components that could be used in any satellite, CubeSat or regular satellite, and also other real-time systems that would be useful for people. And so we're developing it for our new satellite, which is called Lunar Ice Cube. We started with our current one and are redesigning that. There are a lot of design issues because we really didn't have a team looking at the design at the time. And again, this would allow us to integrate Ada or C runtime libraries, and we have this low-level abstraction layer which allows us to be ported to different operating systems and different hardware platforms very easily. So we have intermodule communication. It's designed so the modules are quite independent from each other. We have an asynchronous message passing system, which would be useful in many systems. And runtime library are all going to be verified with Spark. So somebody will be able to use our system knowing that most of the software that they are going to be using, all of ours and whatever they write, can be proven to be correct with Spark. Some of the modules, real-time clock, file system interface, radio communications interface, and support for the CCSDS protocols, which are used by NASA's Deep Space System. Their file transfer protocol has already been done in Spark by one of our students. We know we're going to be using that because a new satellite will be using the NASA Deep Space Network. I was just out at getting trained on their NASA's Advanced Multi-Mission Operations Software, which is their ground software for working with the Deep Space Network, and visited the Deep Space Network sites out in California last month. Some of the advantages we would have: the message passing system is highly concurrent. We made use of this in the file transfer protocol I just described. A lot of runtime flexibility. You can adapt communication patterns at runtime. Sometimes you need to do this. And our architecture is consistent with Ravenscar's for concurrent programming. Some disadvantages. We do have some runtime overhead associated with using this. And because we have to deal with decoded messages and being able to deal with that, that part of it can't be proved with static analysis. At the moment, we don't know how far all of our aspects will be analyzable with Spark. The new version, which was mentioned and is going to be released in the next week or so, will allow us to do some of the Ravenscar concurrency stuff, which we haven't been able to do so far. It's an ongoing effort. It's experimental at this point, but we hope to have it when it's fully developed. The satellite we're working on, so it'll certainly be fully developed when we have to deliver that, which is in about 2.5 years. And we hope it will be useful to people doing other satellite work and other real-time embedded systems. And we hope to make that freely available to people as much as we can with ITAR. There are some issues with that, and so at least in the United States we can make it freely available. Some of the things that you can prevent with Spark Ada is array index out of range, type range violation, and I'll talk about the Ariane 5, which could have used that. Division by zero, numerical overflow, and I'll talk about the Boeing 787 problems. These are two issues which could have been prevented with Spark. Some examples of Spark annotations. Spark annotations are indicated by the double dash indicating an Ada comment, and are thus ignored by the compiler. And then the pound sign indicates this is something that the Spark tool should look at because it has some information of interest to them. So Ariane 5 had an initial flight failure on their, their first flight. And the Boeing 787 has a generator control problem, which I'll talk about. As you can see, the Ariane 5 on the left as it was launched is good, on the right it's not good. 37 seconds later. This is an interesting problem they had. This is software that they actually didn't need to run at all. It was something that was legacy from the Ariane 4. And they didn't do something which I would have thought would have been nice, is to have a file. Okay, here's a file with the characteristics of our launch vehicle. And as we go to a new launch vehicle, we just replace that file, and then the software will refer to the particular numerical values in there to make sure that it's compatible with what's actually happening in the real world. They didn't do this, and it turned out that the Ariane 5 is a larger rocket. It has substantially larger initial acceleration and lateral velocity. At most, you've probably seen rockets taking off. They take off vertically and then start pitching over to get in the direction of the orbit. And they have an angle of attack at that point of generating lift. So they have a lateral and upward direction acceleration and velocity. And they were measuring it, and they had a 6-point floating, 64-bit floating bit point number that was converted to a 16-bit integer. And that worked fine on the Ariane 4, but on the Ariane 5, it exceeded the value in the 16-bit integer and caused an overflow. They had been checking some of the data numbers in this part of the software, which was used for a gyro platform alignment during the first 40 seconds of flight. And if you remember on that side, the slide showing the rocket blowing up, what happened is that they exceeded they had this error which caused their data coming from their system to be completely irrelevant to what was happening in the real world, and their control system then tried to correct to this irrelevant data, had full deflections on their two solid rocket boosters and then their main liquid-fueled engine, causing an increase of the angle of attack over 20 degrees, generating excessive lift, and instead of having one rocket, they then had three, and then the software noticed that that was not what was supposed to happen and initiated the self-destruct. If it had happened 3 seconds later, that software would have been shut down and there wouldn't have been any issue. So it was a very close call. I've heard numbers between 500 million and 700 million for the cost of that failure. I think there were 4 satellites plus the launch vehicle that were lost due to that. Anyway, so that was a problem that could have been prevented. Boeing 787, this was interesting that Boeing never figured this out, but the FAA fortunately decided to have Boeing software running in their lab continuously. And what they found, there's 2 engines on the 787, there are 2 generators on each engine, each controlled by a computer program in Ada, but not Spark. And they were keeping track of the time the power was on in the aircraft. And I've talked to pilots and all kinds of people, you know, airline pilots, and I mean, I'm a pilot myself, and have not been able to figure out a reason to keep track of power on time. Keeping track of the time the engine's running or the generator, that makes sense. But anyway, they're keeping track of power on time, and they're counting in centiseconds. The only people I know who use centiseconds are track coaches with their stopwatches timing their runners, but they're using centiseconds. And it turns out if you keep track of time in centiseconds in a 32-bit register, which is what they're doing, a little after 8 months, the register overflows. Now, the computer then puts the generators in safe mode. Now that, I don't know why the computer thinks that's a safe mode, because that means it turns off the generators. So as you're flying along in your 787, all of a sudden all 4 generators shut off. You lose all your power, that's a complete fly-by-wire aircraft, and you crash. So that's not safe in my idea. I don't know why they call it that way. So the FAA decided for an airworthiness directive to tell them to make sure you turn your power off before 8 months. Where I would have thought, why don't you tell them to fix the code? It literally would take about 5 minutes to fix the code. You know, check that number. If the next time you increment it is going to be too large, reset it to 1, log the time that occurred, and go on. But they didn't do that. Again, Spark would have found that problem for it. There's a Spark book that's now available. So if you're trying to train people, there's our satellite is on the cover of the Spark book, and my colleague Peter Chapin is one of the co-authors, along with John McCormick, who's written a number of Ada books, and there are books in the back. You can go see these things in hard copy. This is the first picture we got back from our satellite. This is the north coast of Western Australia. There's the missing Malaysian airliner. This was pretty exciting to get this picture back. You know, all of a sudden, wow, this is wild. Some other pictures. This is northeast of Perth in Western Australia. Just some pictures of the limb of the Earth. You know, just a little bit of blue atmosphere here that keeps us all in good shape. This one was from June. I have some pictures from last month also. Here's one from September. It's now 2 months ago or whatever. So the thing's still working and sending us pictures. We're talking to it every couple of weeks typically. That's what it looks like. 10 centimeter cube. There's a camera lens right here. It's covered with Kapton tape for vibration tests, GPS antenna, photovoltaic cells. And then there's some LEDs there and there and there and there. The one thing I haven't done yet is I've got to get the software all hooked up on my telescope so my telescope can track the satellite. I've actually seen the satellite with my telescope. I have a 10-inch telescope, and I just pointed it where I knew it was going to be, passing in front of the star Sirius, and at the exact time I see this little dim dot going by. So I'd like to get a video of the LEDs flashing as the satellite goes by. So anyway, we do have LEDs on it, since those boards were made by LED Dynamics for us. Some comments on the first one. We caught errors with Spark that we wouldn't have done that. We didn't have people to check the software, and so the one student who was writing most of the software had the aid of the Spark tools to find errors that may have come up when he was refactoring the software due to changes in hardware or things we found out as we were going along. And the Spark does improve the discipline of the students working on the software. They have to think about things they otherwise might not think about when they're working on the software. And it really helped that. And we certainly would not have completed the project without having Spark. As it was, we completed it a day early, unlike most of the teams that completed it the day they had to walk out of the lab with it and deliver it to the Air Force. And in the bottom it says, although the CubeSat's limited to 1.3 kilograms, the paperwork might be a lot more than that. Literally in the year before I delivered the satellite to the Air Force, I had to write documentation for the Air Force, for NASA, for the FCC. The FCC not only licensed our radios, it licenses the ability to launch the satellite. Some imbecile gave them that power because they don't know what they're doing. I was the first one to deal with them, and it was clear I had no idea what we were supposed to be doing in that aspect. You have to get a license from NOAA to operate your camera. And I was trying to figure out, why do the weather people care if you have a camera? And it turns out they're a front organization for the CIA and the National Reconnaissance Office and the NSA, who don't want their name associated with it. So they just collect the form and they send it on to those organizations and the Department of Defense, who then say, okay, you know, that's all right. I sent my application in early, and about 2 years before the launch, and got an approval from NOAA. And there were 4 other satellites of the 12 on our launch that had cameras, and they sent their application in about 2 months before the launch, and they didn't hear, and they didn't hear. And so finally someone from NASA called NOAA people and said, what's the story on this? Is, there's a national defense directive. You can't have space-to-space imaging capability on non-government satellites. And they said, well, what does it say exactly? Oh, we can't tell you, it's classified. So that resulted in an all-day meeting at the White House with a bunch of White House aides, a high-level person from NOAA, from NASA, and the Department of Defense. And they did the reasonable thing at the end of the day. They gave waivers to the other satellites that were on this launch. And in the future, what they'll do is they'll look at the capabilities of the cameras, and if they think your resolution is really high, that they might worry of you taking pictures of sensitive areas, they're required that you show pictures to them before releasing them publicly. So they have a reasonable solution, which is not always the case for something like this. I wrote about 1,000 pages of documentation in the year before the launch. So I tell my techie students who think they don't have to know how to write, you need to know how to write. This is our new satellite. It's called Lunar Ice Cube, and people were working at Morehead State University in Eastern Kentucky. And they have a fairly active space program. They somehow convinced the state of Kentucky, which doesn't have a lot of money, to build a $50 million space building. And then they used grant money to fill it up with all the equipment they needed, and including outside the building, they have a 21-meter dish. That dish is being converted to be fully compatible with NASA's Deep Space Network. It'll be the first non-governmental node on the DSN. And hopefully that will be able to deal with the majority of CubeSats in the vicinity of the moon. But we also have access for our spacecraft for the big dishes, the 34 and 70 meter dishes that are located in Goldstone, California, Madrid, and Canberra, Australia, if we need them. On the satellite here, we have an ion drive engine here, made just down the road in Natick, Massachusetts, by a company called Busek. There's a printed plastic tank that holds our propellant. We were initially looking at ion drives with xenon, which would have had a 200 to 300 atmosphere high pressure tank. This is just no pressure solid iodine, a little heater to sublimate it as needed to run it through the ion engine. We have 2 star tracker cameras. This is a part of an attitude determination control system that has momentum wheels and the inertial measurement units, as well as the star tracker cameras. The star tracker cameras are pretty interesting. You can just point them at a star anywhere, at any group of stars. They have a database of 22,000 stars. It takes them 7 seconds to figure out what they're pointed at, which I thought was a pretty impressive piece of processing. And so our attitude is pretty important, because the other thing we have here, the primary part of the mission, up here is a 10 by 10 by 15 centimeter infrared spectrometer being developed at Goddard from an existing flying spectrometer that's substantially larger. They're reducing the size of it to fit in this CubeSat. And that has to be pointed at down at the moon when we're taking data. But then we have to rotate, because these 2 patch antennas are X-band 8 to 9 gigahertz range for data transmission and for navigation. The radio, which I think is right up here, is called IRIS. I'll show you. I think I have a picture of it later on. So this is the ion engine in operation. The output grid is about 3 centimeters, just over an inch. The ion has come out at 35,000 meters per second, about 10 times as fast as chemical rocket exhaust. So the efficiency of the rocket is very, very high. We can get an enormous amount of delta V, or velocity change, with a very small amount of propellant. It uses 64 watts, 1.4 millinewtons. It's a very small amount of thrust, so you have to run the engine for a long time. Busek has a very clever design. Instead of having a cathode, which is typically done in an ion engine and is the source of your life limitation as it wears out, there's no cathode. They ionize the iodine with a 2 megahertz RF field. And so the limitation is the wear on the holes in the output grid. And they figure it has a life of about 20,000 hours, which is way beyond what we need. This is our radio, the Iris-2 X-band radio. This is developed at Jet Propulsion Lab. That's a $275,000 radio. It's 10 by 10 by 7 centimeters. It's 4-watt X-band transmitter. But it's all radiation hardened parts. So the parts alone are $130,000. And this has very, very tight specs on latency time for when it receives and transmits as a transponder, because you're using it for navigation, and also very, very tight frequency stability specs because the Doppler shift is also used for the velocity part of the navigation. It also sends the data down that we have. So we rotate it to face the Earth to download the data once we've collected the data on a pass around the moon. We're going to be in a highly elliptical path, the low point of about 100 kilometers, the high point of 5,000 kilometers around the moon. And we'll be orbiting the moon for about 6 months, looking at every bit of the moon's surface during every time of day, looking for water vapor, water ice, and other volatiles that may be coming out of the lunar surface as it heats up in the sunlight. This is the block diagram at the moment, our initial block diagram for the thing, and various types of data lines and various parts here. We have a Proton 400, which is a CPU board from Space Micro that uses a Freescale dual PowerPC core and radiation hardened CPU board. And Burgess is the name of the infrared spectrometer. We have some array of antennas, little rods that were sticking out of the bottom just as a beacon, as a sort of backup radio thing. The lithium radio is the radio from that will be doing the beaconing. Reaction wheels, star trackers, sun sensors. We also have sun sensors on the attitude determination and control. Here's a picture of the launch of our first satellite. This is on a Minotaur 1. The Minotaur 1, the first 2 stages here are from a Minuteman II ballistic missile. So these missiles that were taken out of service during arms reduction treaties are now having some useful purpose. The Russians have done the same thing. Their SS-19, which is the largest ballistic missile ever made, is now called the Dnieper, and that one can launch satellites directly. That had so much weight capacity, they didn't have to do any changes. The Minuteman wouldn't get high enough velocity to get into orbit, and so they replaced the 2 upper stages of the 4 with lower thrust, longer duration rockets made by orbital scientists who put the whole thing together. This is our new launch vehicle. This is the Space Launch System, which NASA is being put together right now. The primary purpose is to test the Orion capsule, which will be up here. It'll fly it around the moon, and it'll come back, the capsule, to the Earth and make a high-speed reentry. It has 2 solid rocket boosters from the Space Shuttle program with additional segments, increasing the thrust by about 30%. The 2 boosters together have about 7.2 million pounds of thrust, just slightly less than the Saturn V, which was 7.5 million pounds of thrust. In addition, there are 4 Space Shuttle main engines there, each with a little over 500,000 pounds of thrust. They're running at 109% of their rated value. They're being tested at that thrust level right now at Stennis down in Mississippi. And so this will be the most powerful rocket ever launched in thrust. It'll be about 9 million pounds altogether. Quite a thing. And so we're going to be somewhere down in this section here, and after the capsule has been separated to orbit the moon, will be spit out. And there are going to be something between 11 and 15 of these 6U CubeSats that will be spit out. There are a number for science missions. We're one of the science missions. There are 3 of them that are currently under competition as technology missions. And so NASA has this CubeQuest challenge, and there are 13 teams vying for the 3 slots. And in addition to getting a slot, they have $5 million in prizes for various aspects of the competition. Here are various people who have helped us, supporting us in various ways. You can see AdaCore and Altran Praxis and so on, SoftCheck, and so on, various people who helped during the system. Okay, any questions?